This is number 2, the back page of, second page of the FRQ Curve Sketching. We're looking at number 2 here. It's from an old FRQ from 1981. All right, so let f be the function defined by f of x equals 12x to the 2/3 minus 4x. Find the intervals on which f is increasing. So if we want to find out where the interval where f is increasing, we can find that through our sine line. So to get to our slope sine line, we're going to find the derivative function first. Set the derivative equal to 0 to find the critical point, critical points, and then test each interval between each of the critical points and look to see the slope behavior of each interval. And then from there we can decide where on which intervals our function is increasing. All right, so first step, we're going to get to our derivative. So first term, we can find that it looks like both terms are set up and ready for us to go through power rule for derivative. So 12x to 2/3, bring the 2/3 down, subtract 1 from the exponent. So 2/3 minus 1, or 2/3 minus 3/3 is negative 1/3. A minus, and then derivative for 4x becomes 4. We have our derivative. We can clean this up a little bit more. So 8 over x to the 1/3 minus 4. We can either set this equal to, when we set the derivative equal to 0, we can either bring the 4 over cross product, or in this case, I think I just went ahead and I found common denominators here. So 8 minus 4x to the 1/3 over x to the 1/3. And here, looks like the critical points come from the numerator as well as the denominator. So the numerator produces 8 minus 4x to the 1/3. We set that equal to 0. Subtract 8 from both sides, and then divide both sides by negative 4. And we get x to the 1/3 equals to 2. And then cube both sides, so x equals 8. Denominator, remember, critical points can also come from the denominator of the derivative. So we set that equal to 0, we get x equals 0. So 2 critical points, we put them on the sine line, and then we can test values in each interval. So here, if I plug negative 1 into the derivative function, I get 8 minus 4, 8 plus 4 over negative. So I get positive over negative, which is negative. If I plug in 1, I get positive over a positive, which is positive. If I plug in value greater than 8, let's say 9, so that will produce a negative in the numerator and a positive in the denominator. So negative over positive is negative. So we see the slope behavior. The graph is decreasing, hits a relative minimum at 0, increases between 0 and 8, hits a relative max at 8, and then decreases to the right of 8. So find intervals where f is increasing. So we know f is increasing from 0 to 8 because f prime is positive. Find x and y coordinates of all relative minimum points. So relative minimum is at x equals 0, and part B, relative max. So x and y coordinates. So we know the relative max is at x equals 8 because the slope changes from positive to negative. And if we want to find the y value, we can plug 8 back into the original function. So 12 times 8 to the 2/3 minus 4 times 8, and then that will reduce down to 16. And don't forget, we need to also write our because statements. Relative max occurs because our slope, our f prime graph, changes from a positive to a negative. So f prime changing from positive to negative. Relative minimum, that's part C. Relative minimum is at x equals 0 because slope changes from negative to positive. And if we want to find the y value, we can plug the 0 back into the original function. So 12 times 0 minus 4 times 0, so 0 minus 0, which is 0. So that's where the relative minimum occurs, at 0, 0, at the origin. Right. Find the intervals where the graph is concave down. So if we want to find concavity, we have to determine critical points first from the second derivative. So we're going to work towards getting to a second derivative function. So I'm going to clean up my f prime a little bit so I can get this set up for power rule to get to the second derivative. So we can bring the x to the 1/3 up to the numerator. So 8x to the negative 1/3 minus 4. Here's our f prime. We can find our f double prime here. Both terms are set up and ready to get to the second derivative using power rule. So bring down the negative 1/3. Subtract 1 from the exponent. So negative 1/3 minus 3/3 is negative 4/3. Negative 4 is a constant, goes to 0. And if we clean this up a little bit, we get negative 8 over 3x to the 4 thirds. Critical point is going to be at 0 if we do cross product here. So it's at 0. If we test values to the left and to the right of the critical point, if I plug negative 1 into the second derivative, I'll get negative over a positive, which is negative. If I plug in 1 into this second derivative, I get negative over a positive, which is also negative. So it looks like there's no points of inflection at 0 because there's no change in signs. So we can say the graph, but part D is asking for not points of inflection, it's asking for when the graph is concave down. So it looks like the graph will be concave down everywhere except at x equals 0. So the graph negative infinity to 0 is concave down, and then from 0 to infinity also concave down. Part E, using the information, sketch the graph on the axis provided. There's no axis here, so I just went ahead and I just sketched out a graph. So if we put information from both sign lines onto one sign line, we know that there's a relative min and a critical point for second derivative at x equals 0. We know there's a relative max at 8. And then I put notations, I put the symbols in each of the intervals so that I know the pairing of the slope and concavity. I know that from negative infinity to 0, the graph is going to be decreasing while maintaining concave down, hits a relative min, and then maintained concave down to the right of 0, but then becomes increasing, and then at 8 relative max, but then maintaining concave down. So the entire graph is concave down. We can plot some points here. We know relative max is 816, so I can plot that point. 0, 0, I can plot that point. So we want the graph, we want the graph to have a sharp point at 0, because we know at 0 the slope does not exist. So we are going to have the graph decreasing, hits a sharp point, maintains concave down all the way throughout, hits a relative max at x equals 8, and then decreases to the right of that while the entire graph maintains concave down shape.